So which product is least likely to form? What do you want to do first, least or most? Okay, which product's most likely to form? A. Why?
Because of the
Markov, yeah.
Yeah, that one. And that leads to lower kinetics at a faster rate because of the tertiary.
Yeah, so here A would proceed through a tertiary cation. Is that the only way that that cation is stabilized, Alexis?
What did you say?
Is that the only way that that cation is stabilized because it's tertiary?
Probably not.
There are also pi electrons in conjugation.
What's that?
There are also pi electrons in conjugation.
Good. Yeah, so there are also pi electron conjugation, right? So we're forming a tertiary cation that's also conjugated with another double bond. Right? So to form A, right, the bromide would add to the tertiary cation. And alternatively, you can imagine a resonance structure. Where the double bond flips up, right? And we form a secondary cation. Okay, so that product is going to be, should be reasonable as well. Does that make sense to everybody why A would be the major product in this reaction? Yeah. Questions about that? Okay, which product is least likely to form? Yeah.
I said B would be least likely to form
Why is that?
due to the fact that it would be the least stable carbocation of all the possible ones, and the fact that it is the anti-Markov.
Good. So it's anti-Markovnikov, and why is it the least stable cation?
It's the only one that isn't part of a conjugated system, and it's a secondary carbocation.
Excellent. Right. So if we think about the addition of HBr, basically just the formation of the double bond, all of the other products except B will lead to a carbocation that's stabilized by pi electron conjugation. Right? This is the only product that would form from an unconjugated positive charge or non-conjugated pi electrons. Right? So obviously we form a secondary carbocation, not conjugated. Bromide would add, that would need to be, but this is going to be least likely to form. Right, we can make a kinetic argument. We could just say that this cation is going to be the slowest, form through the slowest rate of addition. Right? As a result, it will be least abundant at the end of the reaction. Questions? Okay. Class on Wednesday, we were talking about hydrogenation, and we looked at how hydrogen could be added across a double bond using hydrogen gas, right, and a palladium catalyst called palladium on carbon or palladium on charcoal, represented by PD/C. Right, and I said that the palladium is kind of impregnated into this charcoal powder or carbon powder. And so the reaction actually happens, we think, inside the charcoal. We call this heterogeneous catalysis because the palladium is not floating out into the solvent and the reaction happening there, but the reagents are actually floating into the charcoal and interacting with the palladium in the charcoal. When the reaction is done, this is a really clean reaction because when the reaction is done, hydrogen's a gas, right? So we don't have to worry about hydrogen staying in our reaction. And then we can just filter off the palladium on charcoal, and we get our product in the solvent. We rotovap off the solvent, and we just have the product. These reactions, just for the reduction of a double bond, right, as long as there are no other reactive functional groups in our molecule, these reactions are going to be pretty clean. So we don't have to worry about a lot of byproduct formation. Okay, it provides the syn stereoisomer, or the hydrogen atoms are added to the same side of the double bond, right? And we refer to this as being a stereospecific reaction, right? And this is different from stereoselectivity because in stereoselectivity, those reactions are selective for one isomer, right? But we're still making a minor isomer, right? In stereospecific reactions, we're only making one isomer, right? And this is due to the mechanism or the way that the hydrogens are added across the double bond, that it's going to be specific, right? And only make that one isomer. If we submit alkynes to those same conditions, right, we can see that that triple bond is being reduced all the way down to the alkane, right? So both pi bonds are being reduced. Showed something a little different here, just to show that, you know, we can add H2, we can also add D2, right? It's going to be the same thing. D2 is going to be a gas as well. So if we want to add deuterium rather than hydrogen to our molecule, we can do that, right? So this is not specific to alkynes, right? It's just showing a slightly different reagent. Questions about that? So Lindlar's catalyst is a modification to this hydrogenation. And Lindlar's catalyst is palladium on calcium carbonate, right? And then we add in a poison, right? Which oftentimes you'll see as lead acetate, or a molecule called quinoline. So, and what this does is something pretty special, in that it allows us to reduce triple bonds all the way down, or only down to double bonds, using hydrogenation conditions. And it specifically gives us, so we're not taking that triple bond all the way down to that alkyne, all the way down to the alkane, right? The poison basically makes the alkyne reactive, right? But poisons the catalyst so that the alkene is no longer reactive, or the alkene can no longer undergo reduction, right? This is specific for the cis alkene, And that's just based upon, again, the nature of the reaction and how those hydrogens are added. Right, so you can imagine reduction of alkynes down to alkanes, right? This is something maybe we do on the last step of a synthesis, right? If we take an alkyne down to an alkene, we're still keeping those two carbons functional, right? And we can do other chemistry with this alkene once we make it, right? So think about this in the context of a multi-step synthesis, right? If we're starting with an alkyne, we can make an alkene, go on to do other addition chemistry if we need to. Questions? No. Okay. Okay, so next reaction that we're going to learn, next addition reaction, we're not going to go really into depth in this reaction. It's just cyclopropanation. We're adding a carbon across the double bond. This reaction, this specific reaction, is a name reaction. It's called the Simmons-Smith reaction. All right, names, you know, we go over some name reactions. Overall, the names of the reactions are not important, right? It's the transformation or the outcome of the reaction that's important, but if you're interested, it's a name reaction. It involves, again, the addition of a methylene, a CH2 unit across the double bond, all right? Using diiodomethane and then a catalyst in this reaction called a zinc-copper couple. Basically what this does is it makes a zinc carbene. And it makes that carbon of the carbene both nucleophilic and electrophilic. Right, so this is something we went over really briefly in lab, talked about carbenes when we started the N-heterocyclic carbene project. Right, we said that the carbon of the carbene can act both as a nucleophile and an electrophile. Depending upon what's around it, that's going to determine how it reacts first. Right? This would be a zinc carbenoid because it's not a carbene would just have two bonds to carbon, right, and a lone pair. If we have other stuff attached to that carbon that gives it the same property as a carbene, it's not technically a carbene, so it's called a carbenoid. You know, this is one that's it's good to know. We're not going to really go over the mechanism extensively. Just trying to want you to try to understand how these things could come together. If this carbon is nucleophilic and electrophilic, you can imagine, you know, you could get a lone pair adding to the carbon, right, and then the pi electrons going back and making a bond to the carbon of the carbene. So, cyclopropane rings are featured in some pharmaceuticals. So this is a reaction that people carry out industrially. but it's not, I don't know, it's not a reaction that you see a lot of. So, any questions about this? No? Okay. All right, so let's talk about the other two other reactions I want to that are pretty important either for synthesis or just in the grand scheme of organic chemistry. So the first reaction is called ozonolysis. All right, we're going to illustrate on a really simple molecule first. So ozonolysis is a pretty powerful reaction because it's going to introduce some oxygens into our molecule and also break apart the double bond. So carbon 1 of this alkene is going to become an aldehyde carbon, and then carbon 2 is going to become a ketone carbon. Right? And so this isn't to say that all ozonolyses are going to create an aldehyde and a ketone, right? It's going to depend upon what is around that double bond, right? So on carbon 1, what are the things attached to carbon 1 other than the alkene?
The hydrogen
And
the carbon.
a carbon, right? And so in the product, that same hydrogen and that same carbon are going to be attached to the aldehyde carbon, right? So that's why carbon 1 becomes an aldehyde, because it has a hydrogen attached to it, right? It's going to have a hydrogen attached to it in the product. Carbon 2, you can see, is attached to a carbon and another carbon, right? And so in the product, that same carbon 2 will be attached to those two carbons, right? Which gives us a ketone product. Okay, so it depends upon what is around that double bond that determines what type of carbonyl we are going to get. Okay. The reason why we're learning this reaction is because the first step of this reaction is an addition. So we're not going to go through the whole mechanism, unless people really want to. This is my favorite mechanism. Everybody's got to have a favorite. But the first step, so this is the structure of ozone. The first step involves what's called a 3+2 cycloaddition. We're adding something that has 3 atoms, right, to a functional group of 2 atoms. We would draw the arrows, we would show the negative oxygen adding to a carbon on one end of the alkene, pi bond breaking, pi electrons reaching out to the oxygen on the other end of ozone, and then we can satisfy the positive charge by pushing that last pair of pi electrons to the central oxygen. So this 3+2 cycloaddition is why we cover this reaction in this chapter. So see if you could figure out what the product would be if we take this starting material and submit it to ozonolysis. I'll give you a minute or two. How many people got a product? So you still working? You guys need more time? Anybody? What's that?
Another minute.
Another minute, sure. Everybody good? So before we drive the product, let's think about what's happening here whenever we do ozonolysis. So first of all, right, you can see in this scheme above, right, the first thing that we have to think about when we think about the product is that we're breaking the carbon-carbon pi bond. we're replacing not the pi bond, the double bond. And we're replacing the double bond on each of those carbons with a new double bond to oxygen. Right, so this carbon is going to develop a carbonyl. Right, and then the other carbon will also develop a carbonyl. Right, so in terms of figuring out the product, it shouldn't be very hard, right? Because as long as you can understand that, it's not a simple mechanism or a simple reaction necessarily, but the transformation should be easy to figure out, right? It's always going to be the same. Break the carbon-carbon bond, carbon-carbon double bond, whichever carbons were attached by that double bond, you get a new double bond to oxygen.
So I know you probably don't say this, but I was just confused. If you break the double bond, there's still another bond in the ring left, like in the pentaring. Like there's still another connection, so you would separate it into two different compounds.
Correct. Yeah. So yeah, you don't make two things. You're just forming two functional groups. Yeah. Right. So since we have a ring, right, we're just breaking that ring open. We're going to form a chain, and as Frank said, right, both of those carbonyls are still going to be attached at opposite ends of that chain. Right, that's different from what we saw up here, where those two carbons only had one connection point, right? And so when we break them apart, they're going to become two separate molecules. Right, so what's going to be helpful to do is number our carbons in the ring, right? Anytime we go from a ring to a chain, or from a chain to a ring, it's helpful to number things to keep all of your substituents straight. So I'm going to just number the ring carbons. I'll start with one end of the double bond, top 1, 2, 3, 4, 5, right? And so from that, I'm going to draw out a 5-carbon chain, renumber my carbons, 1, 2, 3, 4, and 5, and then start transferring things from starting material structure to the product structure, right? So on carbon 1, what else do I need to draw? Yeah.
Methyl group.
Good, methyl group. And then what is the reaction going to do to carbon 1? Yeah.
Give it a carbonyl.
Good, give it a carbonyl, right? So methyl group on carbon 1, and then carbonyl. Anything on carbon 2?
An ether.
Good, a methoxy group, yep, right? We're going to draw that in. We're going to put a little asterisk there because we're going to have to come back and make sure that the stereochemistry that we represent is correct. Right, carbon 3 you see has 2 hydrogens, carbon 4, 2 hydrogens, and then carbon 5, what do we put on carbon 5?
Yeah, the phenyl group and the carbonyl.
Excellent, phenyl group and a carbonyl. Okay, to make sure that we're getting the correct stereochemistry around carbon 2, we're going to identify what the stereochemistry is in the starting material, right, and then transfer that to the product. So the stereochemistry here, 1, 2, 3, that's going to be the R stereocenter, right, and this carbon that was the alkene is still going to be the second highest priority, right, just like it is over here, so we don't have to change anything, right? Oxygen is 1, carbonyl is 2, then the methylene is 3. So we need this oxygen to be hashed in this case. All right, so we're not changing stereochemistry, we're just kind of creating a new molecule and changing how we're viewing that stereocenter. Right? You can see that carbon 1 is connected to, other than the double bond, is connected to 2 carbons. So in the product, that same carbon will be connected to 2 carbons and form a ketone. Right? And then carbon 5, same thing, other than the double bond, it's connected to 2 carbons, and so in the product, that carbon will also become a ketone. Okay. Questions about ozonolysis? Yeah.
So how do you know which double bond is going to react upon? Like for instance, how would you say like that would react with the phenyl group?
So the phenyl group, remember, doesn't have any double bonds, right? It's a pi system where all 6 electrons are being shared equally, and we draw it like this. So yeah, benzene, it's aromatic, really stable, and so it doesn't react under the same conditions as normal pi bonds. You need some catalyst in there to help it go. Yeah.
I guess going off of what Amanda just said, what if there was a pi bond in the pentaring from carbon 3 to 4? Would that make a difference?
Yes, absolutely. Yeah. So that would undergo ozonolysis as well. You want to try that problem? Yeah.
Hey Joey, this is, I'm helping you.
You're doing, no, you're pushing the rest of us to be good.
You
To be
need
great,
this.
actually.
Will both of them go through?
What's that?
Both the pi bonds will go through osmosis.
What do you think?
Now we break the ring.
Is there no more methyl group on the...
Oh, sorry. Yeah, there's a methyl group there. Thank you. How many people need more time? Everybody? Okay. Frank's going to show us his product, so let me know when we're done. Go for it. No, just the products. You know the numbers. Number what? Yeah, number the carbons. Great, thank you. Right, so when this happens, obviously, we're going to be splitting carbons 3 and 4, right? And splitting carbons 1 and 5. Right? You can see that carbon 3 has a hydrogen on it, so carbon 3 is going to become an aldehyde. Right? Carbon 1 is going to stay a ketone as it was in the product above. Carbon 4 becomes an aldehyde, right? And then carbon 5 is a ketone. So here are the aldehydes, and the ketones are the same. One way that we can think about this is you can see here we have a double bond between carbon 3 and 4. So when this ozonolysis happens, one of the double bonds is going to get cleaved first, right? And then the other double bond will get cleaved. Which one gets cleaved first, you don't have to worry about that, right? But what we can do is think about the formation of one product, right? And then show how that one product is further cleaved with ozone to get to the final two products. Questions about this? Okay. Thanks, Frank.
You still have to send me the pictures for the lab. That's okay. I sent
So I do want to say, I want to encourage questions like that. I think that was a really, really good question that came from curiosity. So I won't make everybody go to the board. I know Frank can handle it. So. All right, so let's end today talking about Diels-Alder. And then we'll come back to this reaction on Monday. So Diels-Alder cycloaddition, or Diels-Alder 4+2 cycloaddition. This is Nobel Prize winning chemistry. So this chemistry was awarded the Nobel Prize way back in the 1950s. So it's been a while. This is one of the most useful reactions that organic chemists have discovered or used for synthesis purposes, because we can use it to form carbon-carbon bonds. And also to make six-membered rings. So mechanistically, let me show the product here. Right, so we're forming a six-membered ring with a double bond. It's 4+2 cycloaddition, right? So we're adding something with 4 carbons to something with 2 carbons. Mechanistically, we have the reason why this reaction works so well is we're forming kind of a aromatic transition state, right? So you can see, and all this really needs is heat, you can see that there are 6 pi electrons moving in a 6-membered transition state. Right, so think about aromaticity, right, and having 6 pi electrons moving around a 6-membered ring. Right, all 6 pi electrons are moving at the same time, right? Draw the transition state like this, it's uncharged. And we form that 6-membered ring. Okay, I'll leave you with this. Right, when these molecules react, right, just like any other bond formation, it involves the overlap of atomic or molecular orbitals on the two molecules. If you think back to when we went over conjugation, we looked at the molecular orbitals or the pi molecular orbitals of 1,3-butadiene. And so if you go back and take a look at those notes, hopefully you can identify this as the highest occupied molecular orbital of 1,3-butadiene, right? Where there's an in-phase interaction between carbons 1 and 2, in-phase interaction between carbons 3 and 4, but an antibonding interaction between carbons 2 and 3. Okay? The LUMO, so that's the HOMO of the diene, is interacting with the LUMO of the dienophile, right? So you can see how these orbitals will line up in order to overlap properly and form a carbon-carbon bond, or two carbon-carbon bonds. Right? When these molecules approach each other, they're approaching each other, one's going to be on top and the other's going to be on bottom, so we can get this specific overlap of pi molecular orbitals, pi bonding orbitals. Okay. Think about this over the weekend. We'll come back to this on Monday. We'll look to see how substitution on diene and dienophile are going to affect the product.